Welcome. All right, so now before we get into our unit on rational functions, I wanted to cover a couple of questions that is going to help you prepare for the unit, something to kind of give you a little bit of that foundation, so therefore you feel a little bit more confident as we start working through the different types of problems and units during this chapter. So what we're going to do is, first of all, kind of go through just some fraction operations, add, subtract, multiply, and division. We're going to kind of review simplifying rational expressions, using the rules of exponents. Then we're going to go back and see factoring. Notice that we've been seeing factoring a lot because I know it's something that you guys always need a lot of help on. So I'll go through a couple more factoring problems. Quite a bit of factoring problems. We're going to go back through the x and y intercepts, this time just focusing on rational expressions. And then we'll look into solving equations when we have rational expressions in there. So let's go ahead and get started to kind of refresh our brain as we prepare for rational functions. All right, so the first one, it's kind of might seem a little obvious for many of you, but it is something that a lot of people forget. If you're not using fractions all the time, you sometimes forget things, or you see something in maybe a little different format and you kind of forgot what you're supposed to do. So in this first one, just remember when you're adding or subtracting fractions, you got to make sure they have common denominators. As long as they have the same denominator, you just add the numerators and keep the denominator the same. In this case, we do not have common denominators, so therefore what we're going to need to do is identify the common denominator. An easy way to do that would be multiplying, just multiplying your products to 4 times 3 to give you 12. That is a common denominator. That doesn't always work. That doesn't always give you work. For instance, like if this was 6 and 2, 12 is not the least common denominator. 6 is the least common denominator. So, but always usually if you get stuck, you can multiply them to at least get a common denominator. So a lot of times what I like to do is just kind of label. My LCD in this case is 12. So what I'm going to do is I'm going to rewrite each fraction with an LCD of 12 while keeping them as what we call equivalent fractions. So to do that, to keep equivalent fractions, I need to multiply by the same number in the top as well as in the denominator. So when I multiply the left side by 3 over 3, I get 3 twelfths. When I multiply the right side by 4 over 4, I get 4 twelfths. So you can see what I did is I devised the value that's going to get my denominator to be the least common denominator. And now I just apply my operation of addition to my numerators, which is going to give me 7 twelfths. And just remember with fractions, we always want to look to, see if you can simplify it further, which in this case we can't, so we're good to go. Let's go and move on to the next one. Now the next one sometimes gets a lot of people tricked up because we see the fractions. So we fraction and we don't, and then we have an integer. So just remember when you're applying fraction operations, we can always write an integer as a fraction by just putting it over 1. So now we have 2/3 really minus 4 over 1. We could say our LCD in this case is going to be the product, but it's also just going to be 3 because 3 and 1 both divide into 3. So therefore, I don't need to do anything to this left side. However, I do need to kind of work on something here on the right side. So therefore, to get 1 to be 3, I'm going to multiply by a 3. I'm not going to put a division symbol there. 3 over 3. Again, that's going to keep my equivalent fraction. So I have a 2/3 minus 12/3. All right, so now when I do 2 minus 12, I'm going to get a negative 10/3. Now, this sometimes tricks people up as well. Like, where does the negative symbol go? Well, just remember, negative 10 over 3 is the same thing as 10 over negative 3, which also is the same thing as a negative 10/3. So you can put the negative symbol in front of it, in the numerator or in the denominator. And if you don't like the numbers I chose, then do 4 over 2. And you'll see if you do negative 4 over 2 or 4 over negative 2, you're going to get the exact same answer. So that is just a random example that I just wanted to bring up because this happens a lot in this chapter, rational functions. People have a really tough time on where does the negative symbol go. So it can go anywhere. It just cannot go in the top and the bottom. Don't do that because that would be a positive 2, right? Or if you had a negative 10 over negative 3, that'd be a positive 10/3. So don't put in both. It's in one or the other, numerator or the denominator, or just put it in front. All right, so with division, we kind of have the same thing. Did I change that? I thought I did change it. No, I guess I I did change. I think this is supposed to be a, I guess I think I had a 2 or 3. All right, I guess we'll just run with that. I thought I changed this. So again, in this case, you can see here we have an integer. So let's go ahead and change this to a fraction. And then just remember, division is kind of like the same thing as dividing by the reciprocal. So the reciprocal of 4/1 is 1/4. So we can rewrite division, usually typically the easier way to deal with division is to rewrite it as the reciprocal. So the reciprocal of, again, 4/1 is 1/4. And now when we're doing multiplication, we're just going to multiply straight across. So that's going to give us a 2/20, which we know that is going to reduce down to 1/10. So I can kind of put some equal signs here. Therefore, you can kind of follow my work. Oh, that's not 1/10, that's going to be 1/5. Make sure when you're reducing the 2/10, 2 divides into the numerator 1 time and 2 divides in the denominator 5 times. So that reduces down to 1/5. And then D here, again, the last example, usually you multiply, straight across. However, just always recommend, always look ahead. We don't want to, you can easily do this. There's nothing wrong with 18/10, but once you just multiply, then you got to simplify. So it's best to sometimes look ahead and see, is there anything I can reduce before? Because we can divide across addition and subtraction. That's called the division property. And we'll talk more about that obviously in this chapter. But in this case, when I have a 2 in the numerator and denominator and they're separated by multiplication, I can just divide those out. Just say 1/1. Therefore, I can just reduce this to 9/5. So you could do it this problem, and you could see 18/5, that reduces to 9/5. And there's nothing wrong with that. But in this chapter, one of the things we always want to look into, simplifying before we apply operations or before we really try to do anything. Because a lot of times when we're dealing with rational functions, something can be simplified to make our life a little bit easier before we do the math. All right, now let's just kind of go back through our rules of exponents, something we spend a lot of time in Algebra 1, Algebra 2. I'm not going to go through the the multiplication, division, or the product, the quotient, the power rule, power to product, power to quotient. There's all those kind of rules that you just want to remember. So I'm just going to kind of go through different parts. But if you need a big refresher, make sure you kind of check, go back over that. So in this case, we're just going to simplify. We're just trying to reduce this down to the simplest quantity. So first thing is, one thing that's kind of helpful, I think, is just separating the numbers and the variables. Just kind of combining like terms. You can only combine x's with x's and y's with y's. Well, we're only going to be able to simplify the numbers and the variables. And the same thing, you can only simplify x's with x's and y's with y's. So obviously, I keep everything kind of consistent here, but what we'll want to do is just, think about this as 2 separate problems. Can we reduce 2/4? Yeah, we can reduce that as 1/2. And you can just kind of break this out as multiply. And then can we reduce x squared over x to the 3rd? Just to kind of do a quick review. Remember, x squared is x times x. X cubed is x times x times x. So therefore, you're just going to leave ourselves with a 1/x. You might say, well, where'd the 1 go? Well, as you divide these out, right, there's still a 1 there. You just can't say there's nothing in the numerator. There's always going to be a 1 represented there. So we can just represent that as 1/x. If you remember the quotient rule of exponents, that is to subtract the powers, and that's why that works. 2 minus 3 is going to be a -1, and if you remember, negative is going to put that in our x to the -1 would put that in the denominator. So we'd have 1/2x. And then next example, we have 3/2, which cannot be reduced, so I'm just going to leave that as is. And here you see x squared over x squared, that just reduces to 1/1. They divide each other out. So we're just going to be left with 3/2. In the next one here, this one sometimes, you have 6 divided by 2, which reduces to 3. To keep things kind of consistent here, I'm just going to do 3/1, just divide out a 2 in the numerator and the denominator, just so I can kind of make sure I still have a numerator and denominator. And then this one, you could say, you have an x cubed over x, that's really x to the 1st power. So 3 minus 1 is 2. But again, notice you have more x's in the numerator than in the denominator, right? So therefore, you're going to be left with a x squared. We really don't need to represent the 1 in the denominator. So we'll just write this as 3x squared. And the last one just kind of goes into, we have still kind of rules of exponents, but now we're not dealing with a a monomial, we have basically a quantity raised to a power and in the numerator and the denominator. But again, just treat this like it wasn't, forget about the x plus 1. Let's just pretend this was x. If this was x cubed over x squared, we would just get x, right? You're subtracting the powers. 3 minus 2 is 1. So in this case, we're going to have x plus 1 to the first power, which we don't really need to write that 1 there, but we can just leave it as that. So just remember, even if we, start seeing quantities, polynomials, which we are going to be doing in this chapter, follow a lot of what you remember, what you've been taught from the rules of exponents to follow along. All right, so factoring is huge in this chapter. We are going to want to make sure, obviously, we covered factoring in functions. We covered factoring in polynomials. And in rational expressions, it's just, it should be hopefully at this point, some rote memorization. You should really be able to look at a problem and know which factoring technique you're going to want to apply. So up here we have factor the following expressions. We have 4x squared plus 3x. Notice we always want to look for a common quantity or GCF to factor out first. In this case, I see I can factor out an x, so I'm just going to do that. I don't see anything in terms of the numbers that I can factor out. So, and again, remember factoring is just rewriting the expression as a product. So this was typically two terms were separated by addition, and then I've now rewritten this as x times 4x plus 3. You can always check your work by multiplying your factored out term back through using distributive property just to make sure you get it right. All right, in this case, we see that they have a common term of an x as well as a common term of a 2. So therefore, I'm going to factor out a 2 and an x, and I'm left with an x minus 3. The next one here, again, we have a trinomial. We've worked on this before. So in this case, I'm looking for what two numbers multiply to give me a -4, but then add to give me a -3. Thinking through the factors of -4, that would add to give me -3. I'm coming up with x minus 4 times x plus 1. The next one is, again, really the same numbers, but now I'm just making that a +3. So again, my point here was to try to say, all right, the middle term is positive. That means I want my larger factor to be positive, of 4 to be positive. So this is now just going to turn to x plus 4 times x minus 1. And again, remember the 4 and the 1 has to be positive, 1 has to be negative because their product is a negative. In this case here, we have a common factor of 4. So I'm just going to factor that out and look at it. So I have x squared minus 4. And here I recognize I can factor that using the difference of two squares. So this will be x minus 2 times x plus 2. All right, in this example, this one's kind of a nice one because this comes up and it throws everybody off. They, get to the factor and they're like, all right, got it. And then here we go. Here's a problem where everything's switched around. So the first thing I tell you to do is we like factoring, or at least all these problems. You notice how x squared, is always in descending order. X squared, is first, then the middle, then the linear quantity x, and then a number. So let's go ahead and rewrite this like this. Remember that 9 is positive, so that's why we're going to put a plus in front, right? That's a positive 9. Then I recognize, well, I have a negative x squared. When we're factoring, typically it's easier to factor when the first term is a positive 1. So therefore, I'm going to want to factor out a negative 1 technically. That's going to give me a positive x squared minus 9. Now I see this as a difference of two squares. So this would be an x minus 3 times x plus 3. And there you go. Next one, what you need to know. So, I don't know what I'm doing. Let's continue factoring. All right, in the next one, I kind of recognize this as a perfect square trinomial. I see 36 and I say, that's a perfect square. And then I look at the middle term and I say, 36 is a perfect square of 6, right? And if I double 6, I get 12. So this looks like a x plus 6 times x plus 6 because my middle term is positive. And then I could simplify that even further into x plus 6 squared. For this chapter, though, since we're going to be doing a lot of simplifying, I would hold off on doing the squared term. Just sometimes, it's not as bad, but I think sometimes expanding it all out, you'll be able to see how things divide out and simplify a little bit easier. For h here, looks like we have a common factor of 3. So let's go ahead and factor that out. So that gives me x squared minus 2x. Plus 1. Again, looks like this is another perfect square trinomial. So let's do this as x minus 1 squared, even though I just said you don't need to do it. Just for simplistic and shortening time, I'll factor that as a binomial squared. All right, here comes another one where we have a coefficient, and I know my trinomials are going to be factored down to a product of two binomials. I can't factor out a common term, so I am just going to set this up as a product of two binomials that I at least know that will work. 2x and x, right? 2x times x gives me 2x squared. Now I got to think about what two numbers are going to multiply to give me a -2, but then add to give me a +3. So immediately I think, well, if I did 2 times 2, that's 4, and I would just need to subtract 1 here to get to 3. So how could I get to 4? Well, I could get to a +4 by having that as my factor. So 2 times what gives you -2? Well, that has to be -1. So again, let's just check our work. 2x times x is 2x squared. -1 times 2 is -2. Let's check our middle and our outside terms. That gives me -x. That gives me 4x, which would 4x minus x would give you 3x. So boom, works. All right, now getting on to the x and the y intercept. So we worked on this obviously in the polynomials, and we talked about it a little bit in the functions. So again, the same rules apply. It doesn't matter if this is a rational expression or if it's a polynomial. If I want to find the x-intercept, then y needs to equal 0. If I want to find the y-intercept, then x needs to equal 0. Now, rational functions come with a little bit here differences as far as how to solve them. So that's why I wanted to make sure we spent some time just going back over our order of operations. Did I give myself? I should give myself some more room. Let's go back through these order of operations to make sure we have this. All right. So if I want to find the x-intercept, then I'm going to make y equal to 0. Now, you might say, well, where's y? Well, typically, this is in function notation, right? So function f of x is representing our y value, which could also be looked at as y. So I could have represented these as equations. I used function notation because that's something that is, sometimes we'll see, but this could also be the f of x axis. So furthermore, and also in this case, I call it the y-axis. So anyways, if I want to find the x-intercept, I'm going to replace y with 0. So therefore, I have 0 equals 1 over x minus 3. I guess, did I give myself? Yeah, I made it work here, but probably definitely should have given myself some more space. All right, so using our inverse operations here to isolate my x, I need to add 3. Okay, so then I have 3 is equal to 1 over x. Now to get x off the denominator to solve, I need to multiply by an x on both sides. That leaves me with a 3x is equal to 0. And then just to solve for x, I will undo multiplying by 3 by dividing by 3, and I get x is equal to 0. So something you might have been able to recognize a little bit later, and that's kind of the point for you to do some of these problems so you can start seeing some of the patterns that are occurring. Now let's go and get on the y-intercept. So the y-intercept is just going to be when x is equal to 0. Now this comes into something kind of interesting. Well, now we have 0 in the denominator. And if you remember from our functions unit, 0 cannot be in the denominator. So what is the y-intercept then when 0 is in the denominator when it can't be there, right? Well, that is actually no y-intercept. Or sorry, yeah, no y-intercept. And once we start taking a look at the graphs, you'll kind of see how that makes sense. And then at the end of this course, it will make a lot more sense as far as what that produces and what is going on. For right now, we just want to make sure we understand that there's no y-intercept exist when 0 is in the denominator. All right, so let's go do another one here. So for this one, x-intercept, so we're going to put 0 equals 1 over x minus 2. Now here, my quantity is x minus 2. So previously, like when my quantity was, x, I multiply by x on both sides. Well, now I'm going to need to multiply by an x minus 2 on both sides. Again, x minus 2 times 0 is just going to give you 0. X minus 2 divided by x minus 2 is just going to give you 1. Now again, here comes up to an interesting thing. 0 equals 1. Well, 0 does not equal 1, right? 0 never equals 1. So therefore, that is an incorrect statement. So since in this equation, trying to solve for x produce an incorrect statement, that would be a way that shows us, again, just like with no y-intercept, we can also have no x-intercept. So here's an example of where there'd be no x-intercept. And again, once we look at the graphs, this will make a little bit more sense. All right, let's go ahead and look at the y-intercept. All right, now when looking at the y-intercept, we're going to do the same thing here. So we'll have y is equal to 1 over 0 minus 2. Well, this one's pretty easy. 0 minus 2 is negative 2. So y equals a negative 1/2. All right, next example here, we have x-intercept. So the x-intercept is going to be 0 equals 2 divided by x minus 1 plus 3. All right, so in this example, again, we got to be very careful with our order of operations, right? We can't do it. We can't multiply by x minus 1 before we get rid of this 3. So we're going to need to subtract by 3 first. All right, so I get a negative 3 equals 2 over x minus 1. Now that I have my fraction isolated on the side, now I can multiply by its denominator to get the x off the denominator. So I'm going to need to multiply by an x minus 1. So therefore, I'm left with a negative 3 times x minus 1 is equal to 2. Now I'm going to want to apply distributive property here. I didn't do it just because I wanted to make sure you guys could see my steps, but I get a negative 3x plus 3 is equal to 2. All right, now it just goes into using inverse operations to go ahead and solve. So let's see, if I subtract a 3, I get a negative 3x equals negative 1, and then divide by 3, or divide by negative 3, and I get x is equal to positive 1/3. I think that's what I got. Yep, very good. All right, so now let's go and look into the y-intercept. So now looking into the y-intercept, I'm going to have y is equal to 2 over 0 minus 1 plus 3. So 2 divided by negative, so 0 minus 1 is negative 1, right? 2 divided by negative 1 gives you a negative 2 plus 3. So y is equal to 1. Now again, sometimes this might be a fraction, so therefore you'd have to combine like terms. I decided not to do one of those because we're going to be doing them during this unit. All right, last but not least, what we want to cover here is solving equations. So one of the things we're going to be doing is solving equations with rational functions, or rational equations, or rational expressions, whatever. So the main thing that we want to look at is when we're solving x, I think at this point we're comfortable with knowing that we need to isolate the x, right? The x needs to be by itself isolated. So we need to use inverse operations, reverse order of operations to isolate the x. And at this point, you should have enough experience doing that. One thing, though, that often gets forgotten is, especially when we're doing rational equations, is remembering you can't solve for x when it's in the denominator. So we have to get the x off the denominator. So there was a couple examples where I did this in the solving for the x and y-intercept. See here, my x was in the denominator. So to get rid of my x, I multiplied by an x on both sides. By doing that, that's supposed to be a 1/3. I made a mistake. Good catch. Okay, so by multiplying here by x, that gives me a 1. And then I divided by a 3. So therefore, that gave me a 1/3. Good catch. Glad I went back. And then the other time when we looked at it, was over here and over here. In these examples, we had quantities in x in the denominator. So to get the x off the denominator, we multiplied by the quantity in the denominator on both sides. So we're going to work through a lot of different problems. It's not always going to be as cut and dry as whatever's in the denominator you multiply by. There are some tricks like cross multiplication that sometimes is useful. In this case, I am just going to avoid that because I like to avoid that in my instruction. And once we kind of understand, again, our purpose and what we're trying to do, then I go ahead and, we look into some shortcuts and stuff like that. So for right now, though, I think our main idea is we need to recognize that we have a variable in the denominator for each of these problems. We need to get the variable off the denominator. That's our first step. Then we can utilize solving techniques or the solving equations, techniques to solve different types of equations. So in this first example, in this first example here, I see I have an x in the denominator. So therefore, I'm just going to multiply by an x on both sides. And actually, this is the exact same problem that I had over there. I'm not sure if I did that on purpose or not. So hopefully this was an easy one for you, but you can see the process that I had to go through to get that. I probably should have picked some different numbers, but that's okay. So x equals 1/3, all done. That was easy. The next one, we have an x in the denominator. Again, let's just go through the same process. If I want to get this x out the denominator, I'm going to multiply by an x on both sides. The x is divided out over here, so that's going to leave me with a 2 over a x squared divided by 4. Now, if I want to divide by 4, divide by 2. Now, if I want to solve for x squared, I need to get the 2 off the denominator, so I'm going to multiply by 2 on both sides. That gives me a 4 equals x squared. Oh, one thing I forgot. Now, to solve for my x squared, I'm going to now need to do the inverse operation of squaring, which is the square root. So when I square both sides, just remember to keep introduce the square root. Make sure you take the positive as well as the negative solution. So that's going to be plus or minus 2 equals x. And the reason why we got to make sure is, when we're doing rational expressions, it's very important that we go back and check our answer. This was something that we used to do in, when you're first learning how to solve equations, so you guys could see that the solutions that you found made sense. It's really, really important for rational expressions because if you, what you call, there are going to be what we call extraneous solutions that we solve, but actually don't make the equation true. So for instance, like, does this work? Is 3 equal to 1 over 1/3? Well, remember, if you were to simplify that, you'd multiply by the reciprocal. That goes to 1, and 3 over 1 over 3 is 3 is equal to 3. Check. Here is 2 over 2 equal to 2 over 2. Yep. What about 2 over negative 2 is equal to negative 2 over 2? And yes, that one works as well. So it's very important. If you don't take the plus or minus, you lost this solution, right? If you just said, oh, the square root of 4 is 2. It's also negative 2. You can see that both these solutions work. So, like on a test or a multiple choice, that would be a solution that you'd have to make sure that you understood where it came from and that it's not extraneous or that it's at least there. All right, the last one here is now we have 2 x's in the denominator. And they're in quantities. They're not, as a monomial. But hopefully you kind of recognize we really need to do the same thing. We need to get the x minus 3 off the denominator, and we need to get the x minus 1 off the denominator. Now, we could look at this in terms of like fractions. Basically, the way that I like to teach this is finding the LCD and multiplying everything by the LCD. But you could also just look at this as, well, to get x minus 3 off the denominator, I need to multiply by x minus 3. But remember, you just can't do that on the left side. You have to do that on the right side. And then you say on the right side, well, to get x minus 1 off the denominator, I need to multiply by x minus 1. So then you multiply by x minus 1 on the right side. So, and if you notice that the product of these two denominators is actually the LCD. So once you feel more comfortable with identifying the LCD, you can look at the denominators of a rational equation, identify the LCD, multiply everything by the LCD, and what that's going to do is that's going to get rid of your rational expressions. So in this case, my x minus 3's divide out, and my x minus 1's divide out, leaving me with 2 times x minus 1 is equal to 4 times x minus 3. Now, again, I'm just going to apply distributive property here, and I get a 2x minus 2 equals a 4x minus 12. Now, I'm just going to go ahead and combine like terms. Minus a 2x, minus a 2x. And therefore, it looks like 10x is equal to 2x, divided by 2, divided by 2. Sorry, I'm covering myself up. And we could say x is equal to 5. And again, we just want to make sure, that this works, that it's not an extraneous solution. And so when we plug in 5, 2 into 5 minus 3, and a lot of times you can just do this in your head. I don't require my students to always, show their work for extraneous solutions. And we get 2 over, let's see, that's going to be 2 over 2. And in this case, we get 4 over 4, which again, 2 over 2 is 1, 4 over 4 is 1. So there you go, ladies and gentlemen. That is a couple set of problems to kind of get you prepared for our rational expressions. Again, just a review here, we worked on solving rational expressions by basically getting the variable off the denominator. We looked at determining the x and y intercepts by setting x equal to 0 and y equal to 0. We practice factoring, a lot of different factoring techniques, because that is something very big in this chapter. Then we looked at just using the rules of exponents to simplify an expression, and then looked at factoring operations, because that's basically what rational expressions are. They're just fractions with polynomials in the numerator and the denominator. So this isn't everything you need to know, but hopefully this is a good start to refresh some of the things that you've previously learned, or to add things that you maybe never learned to help prepare you for rational expressions. So now the time is to get started with rational expressions. Cheers.